That's right.
Or it might not count at least.
Yeah, it might not. Yeah.
Yeah.
Number 3.
You have to take a final.
I know.
You'll be the control. Okay, so we are starting up the in-class problem solving for assignment 14. Why does it say A01 in class? That doesn't sound good.
Okay.
Yeah, that's what I thought.
It is A01 in class. That's weird.
Imran, you worked.
Let me put this back to 14.
There we go.
There we go. I'll have to fix that link. So these are the problems we are solving, and Duncan, you can grab one of these.
I'm a cow bear.
And hopefully there's a marker there. I will pause until people actually get some progress. So how did we go from circuits to zoos?
I'm trying to okay.
So Emma's doing number 53.
Our average power for a resistor is V squared over 2R, right?
Average power for a resistor, if it's V magnitude, are they talking RMS or are they talking, which one are you doing?
I'm doing number 11.3.
So load consists of, load's going to a voltage source. Yeah, they're giving you the magnitude. Find the average power delivered to the load. Yep. Mm-hmm.
So it's just V squared over 2R, right?
Yep.
What's that capacitor have to do with anything? Because I would need to convert this to...
Focus. Well, it could just be a distraction.
Could be.
That's happens sometimes.
It says the answer is 13.33. Well, let's convert.
V squared, so 40 squared, 1600 over 120. 1600 over 120. That's probably about right?
40 squared divided by 60 is 266.
It's 120 though. 40 squared over 120, not 60.
Oh, you're right. So 40 squared divided by 120, 13.33. This is beneath an squared over 2R.
At least you're going to help those pompous MIT people laugh at themselves when you get there.
Yeah. I'm going to find the AMRA of the group, and I'm going to be like, listen here, I'm going to need you to do my homework for me.
I'm not sure when I stopped recording. What are the minutes here? Did I not turn this thing on? Come on.
Look at her. Still working on her first problem. Is it a tough one?
It is a hard one.
It's tough for me at least.
Maybe it'll be easy for you. Why don't you help her out?
Oh, I don't want to hold someone's hand. That's not the MIT way.
They want me to, I showed my skateboard to my boss at Mate.
Mm-hmm.
And they're like a marine.
Yeah.
All right, it looks like we're recording now. Anyway, none of that was being recorded, so I think, so I don't know what it should off. Anyway.
So the first thing we were trying to find was Z Thevenin.
Mm-hmm.
So we applied a test 1 volt source.
Yep.
Meaning that we have to find the current going here, so we can do V over I to find R Thevenin.
Yep.
Or Z Thevenin or whatever. So first thing we did was we found VO so that we would know this current.
You did a nodal equation right at VO, right?
So we found VO, so we know that the current here is 2 times VO. Now we're doing KCL on this node right here to find what our current is. We know that, so I gave that variable, that current, the name IX, so I know that IX plus 2VO minus I equals 0.
Plus I.
Is it plus I?
Well, are you summing all the current going into the nodes?
You're right. Okay. We'll figure that.
And so you found VO is what you're saying, and now you're trying to find, yes.
So I wasn't sure about the VO because this J value is here. And I don't know.
Well, you can clean that up a little bit, right? I mean, you could put that in phasor form. It might be nicer. You can multiply top and bottom by the complex conjugate, so 2 plus J over 2 plus J.
Yeah.
Yeah, but
But now this is, I mean, and we can do that anyway. I was just getting, before I get to the heavy algebra, I wanted to do the circuits part.
Yeah, no, that's cool.
So now I have my Ix was equal to VO minus 1 over negative J.
Yes.
Based off that. And,
Yep.
and then I have my 2VO is going to be 2 over 2 minus J.
That makes sense, yeah.
Right here. Equals negative I.
Yeah.
So now we can do algebra.
Sure. Yeah. Good.
Cool.
Yeah, that sounds great. It'll be good. Duncan's doing it a different way, and you might check this out because when you have a did you get already? You guys want to see what Duncan's doing? Hey, you guys want to see? Why don't you see how he's doing it?
Okay.
So this is what I'm getting for the equivalent to these two.
In parallel, J times minus J over J minus J.
Yeah.
Oh, that's not good. Oh, you know what? I wonder if that's a resonant circuit. It might be resonant
When are
there.
we going to get to resonance?
Next week.
Are we involved?
So you're dividing by 0 then. How do you deal with that? That is not good, right? You got a J and a minus J. Darn it. Well, maybe they will run into the same problem.
Cal Poly and IT grad. Want to just cross multiply things? That probably did first.
So those cancel out. That means it's infinity, right?
Yeah. So it'd be
It's like an open circuit.
circuit. So then
Minus 1.
V0 would just equal.
Minus J. Is that right? Plus 2.
V0 would just equal that, yeah. Yeah, I'd say let's go with that, right? Let's say, so V0 is 120, and then IN is,
Let's get this together.
So why don't you multiply?
how do you have IN being 2V0? Is that because of this over here?
Oh wait, top and bottom by minus
Well,
J
no,
minus J over here.
wait.
Cross multiply.
Yeah, that's not a good way to go. That is kind of confusing, right? Well, IN, because isn't there going to be some current going this way too?
On both sides by having the top.
It's going to be
But the way I
2VO.
like one of the few things, it's like, so you take the denominator.
Yeah, but let's see, you've got, you're still finding VO, right?
So it doesn't make a difference.
All right, so let's see. If we do top and bottom here.
You're saying VO is basically 120, right?
Yeah.
Minus
So you've got 120 here, and then you are going to get current going, because this is ground here, right, too? So you're going to have 120 over minus J2 of current going that way. So IN would have to be 2VO plus,
plus this is going to be negative J2.
maybe this isn't the best way to go, but
Negative J2. That's negative plus 1. Right? Yeah. All right, so now.
are you going to get out of divide by 0? Who knows, right? So 2VO,
Minus 2 plus J, so it's going to be minus. So that's just going to be minus 1 plus J. And this is going to be 1 minus 2J. I keep going back and forth. I need to get like consistent.
by the way, when J times minus J is, that's plus 1, right?
Yeah.
So it's 1 over infinity. So it's basically, or 1 over 0, so it is positive infinity. But it would be interesting if it was like J over 0, then you would have some, what would that be? I mean, I guess that would still be an open circuit, but I guess we don't have to deal with that. So let's keep going.
Equals 0. And this is wait, equals negative I. Okay, great. So now 1 by negative 1.
So is that 240 plus 120 angle 90?
Let's do the complex conjugate. Which
And that would be 240 plus 120J.
Yep.
So that's good. And Rod, you're doing the power going from, isn't it it's kVA, not kVARs, right?
Minus 2.
Oh.
And kVA means that's S. That's the hypotenuse of the triangle. Just you might have been doing it that way, but just so you.
I was gone a long way.
And this one though is receiving VARs, so 500 VARs. So this is P and that's Q, and these are S and S. And this is going to tell you the angle. Now, when it's leading or lagging, this is the thing that's kind of confusing in this part. You have a marker here? Because the
Or make it like negative.
when you have a lagging power factor, what that's telling you is because Eli, current voltage leads the current, and the lagging means that the current is lagging the voltage. So that means it's inductive. And with inductive loads, it's because the Z is R and X for an inductor is J omega L, and theta is greater than 0. So theta is greater than 0 for inductive loads. When it's leading, that's ice, current leads the voltage. And
So that's negative. Just put a minus in here.
and the impedance of a capacitor is capacitors have negative reactance.
This minus I can't.
So it's X, this is sort of an XL, and this is XC is minus J over omega C. So the angle is going to be less than 0.
Yeah, that's maybe 6.
Yeah, so the signs are going to be important when you add those together. And then given P and Q, you can find the angle as well, right? Just draw the power triangle and find that. And that's a positive 500 bars, so that would be. Yeah, just find the angle of that. Actually, make sure that's 1,000. It's the units, right? Yeah.
So it's 2 times 2 is 4, and J times J is -1 and minus.
So you got an R Thevenin or Z Thevenin? You got 60 root 2. That was that's your initial, that's your V Thevenin, right? Wait, didn't you find that V Thevenin is this? Shouldn't it be that? It should be this. That was your VO when you had an open circuit here, and then you had to find V Thevenin based on VO using this, right? So it should be that over that.
It's voltage over current, right?
I'm not sure. Tom, question.
Yeah, question?
To find R Thevenin, you do voltage divided by current, right? The test voltage divided by
Yes,
test
both
current.
V Thevenin or Z Thevenin, the impedance is
Z Thevenin is going to be equal to V over I.
V Thevenin over I Norton, or V Thevenin, or your test voltage, right? V test over I test,
Yeah,
right?
So it's going to be 1.
Test.
So it's going to be 1 over that
Yeah,
expression.
which is going to be 5 over that.
Dude, we just did the conjugate for no reason.
Now you gotta do it again. Or go back to this. Wait, where did you do the conjugate?
Here, right here.
So it was 1 minus J over 1 minus 2J?
Yeah, I think we'll just do it all over
Since you're doing the reciprocal, oh well, whatever.
Minus 3 plus.
You can always use experience doing conjugates. How's it going over here? Is it,
I don't know.
I think we should have just left it.
So minus 15.
so you found theta C
Yeah.
as, what, 26.56 degrees? Okay. So the thing is, once you get the how do we do this? Once we get the power, let's see. So
So we have Z Thevenin. Can we check that?
so we know it's 120 angle 30 over here, right? And we know, so that we know that's V. And we know the voltage, and so we can figure out if we know the power, right? We can figure out what I is, right? Because
Well, that's not the value.
so you figure out what IB is,
The value of Z Thevenin.
Okay.
because the power is, and essentially you can now write complex power, right? Now that you know SA and theta A, then your complex power A is S angle
nothing.
theta
I'm gonna
A,
tell
right?
Tom to report this so I can erase it, and we'll just like.
So that is, what was that again? 4,000 angle minus 36.87. And that equals the phasor voltage times the complex conjugate of IA over 2.
Right.
So you can find IA, because you know V is 120 angle 30. So you can find IA that way.
Okay.
And then you, knowing we should, no, because IA is in, because IA is in series, or the source A is in series with, what I just said applies to B.
Okay.
So B, because B has that voltage right across it, right?
So I couldn't do this.
Don't have to
What I
check
did
the
there.
whole thing,
I just,
What was this?
electric straightforward.
I got the magnitude of.
You got the magnitude as 40 amps? How'd you do that?
Yeah.
There's a lot of ways of doing these things. So S was VMI over 2, 2400. So 60 IM. Yeah, I think that's probably right. But then it would be helpful to know the phase angle.
Yeah.
And I think that will just fall out pretty easily, right? So with SB, so you've got SB is 120 angle 30 times IB star over 2. And these are not RMS. Is that an RMS value for that 120? Okay. And you've already found out that this is 2400 with an angle of 53.13 degrees.
Tell me you get a chance.
Okay, so now you should be able to find IB.
Okay.
And then from there, if you know IB, for these guys, what are we trying to find I? What are we trying to find here? We're trying to find I. Yeah. So for these guys, you know the power, and you can add those powers. So you can find a net, the net power of both of these things.
Really?
Yes, because the power is additive. Remember, the power of each of the components add. Now, when you have different phase angles, you're going to add those phasors as complex numbers, and you're going to get a net power. And that net power is going to be, you know, SAC. And again, you can use that to find your IA.
Okay.
That's how you do it. Yeah.
So I just, well, we found our Z Thevenin, but I need more room to work. So
Check with Duncan, because he's doing the same problem.
Well, no, I don't need help. I just wanted you to.
But I want to see if they compare.
I just wanted you to get a picture so I can erase it because I need more canvas. from my art.
Yeah, darn. It's too bad you
found
ran out of
my-
room. So you found, what did you get for Z Thevenin, Duncan?
This is
Let's just see if you guys have consistency, because we don't have any intermediate values here.
Yeah, we don't.
And you guys should agree. What'd you get? 0.7 with an angle of 49 degrees? What'd you guys get?
Oh,
We left it in complex.
Can you turn it into polar form, just so you see if we have a comparison?
Yeah, sure. Where's my polar sheet?
let's divide it by 10.
Or multiply by 10?
Yeah.
Let me get my little help sheet, my handy dandy help sheet.
Don't we just like square the value?
And call me over when you get something. I'll check in on Ron here. How's it going?
A plus BI. I just part of it. Just
Good. Did you find a theta C?
Alright, so let's see.
Theta
We
C.
want to find.
Yeah, you can find the angle here, right? That would be the arctangent of 500 over 1,000.
Well, first let's.
That would
Okay,
be
I'm
theta.
fine.
Oh, theta 1, theta 2, theta 3, or whatever.
Okay.
Yeah.
No, it's just going to be negative 15 over 10 plus 1/2 j.
Yeah.
Yeah.
So the square root of,
So the square root of those two numbers.
here, I don't know how to use your calculator.
That's
I don't think it's, well, he had 0.7. Would that be, I think you're going to be more than 1, right?
So negative 15.
Yeah, it's going to be more than 1.
Divided by 10 squared plus 25 squared. Square root of that. 1.58.
1.58
1.58.
See if the angles.
How confident are you in your results?
Not very good. And our angle is the tan of that, so B. So it's 0.5 divided by.
Okay, so let me just kind of chase your work here and see, because you don't want to erase it if you made a mistake
And then
earlier. That's the problem.
Of that, and my theta is negative 18.43.
Okay, that's way out. That's
I mean, it is certainly possible that we thought.
You know what? Here's another way to find VO, and let's try that, because you did a nodal thing.
Mm-hmm.
But again, this is a situation where you have a known voltage being applied across two series impedances, right? You've got this impedance and this parallel combination. So you could do the voltage divider formula. And that's a good thing to do. That'll give you another way of calculating VO, and you can see if you get the same VO as you had there.
So it's going to be, it's just going to be.
It's going to be 1 volt
one
times this parallel over minus J plus this parallel. That's a pretty easy calculation to do, I think, right? Let's just try that real fast.
Yeah,
So let's hash it out here. So we got, so VO.
You want me to?
No, I got it. So give me a new marker. Throw this thing away. So using the voltage divider equation, VO equals 1 times, well, actually, let's find Z parallel is going to be 1 times J over 1 plus J.
Which can be J over 1 plus J, which is
times 1 minus J.
minus J.
That's just 2, right? So it's J.
Yeah, 2.
It's J plus 1 over 2. Or 1 plus J over 2. That looks sort of like what you had, sort of like over there. So, so that becomes 1 times, that's VO, or that's this voltage here, right? That 1 volt times 1 plus J over 2 over.
now we gotta add the minus J
Over
to
minus.
the Z parallel.
Yeah, you're going to add that, so you're going to have 1 plus J over 2 plus or minus J there, right?
Plus or minus J, yeah.
So that equals 1 times, well, how are we going to do this? So 1 plus J over 2 minus J is minus 2J over 2 is going to be 1 minus J over 2, right? So it's going to be 1 times 1 plus J over 2. And this is going to be just 2 over 1 minus J, which is going to equal 1 plus J over 1 minus J, which is going to equal this is going to be 2 again, right, on the bottom. So that's going to equal 1 minus J squared is plus 1, right? So that's going to be 2, and that's J plus 2J. So it's going to be basically 1 plus J, right? Now, if you had done this and turned this into a standard form, you'd have to multiply by 2 minus
2 plus J.
2 plus J, thank you. So that would be 2 plus J over 5, which looks different. So it would be interesting to see if there's an error here. The nice thing about whenever you can do that voltage divider formula, it's a lot simpler, right? The algebra is a lot simpler.
So let's see, where
But we could still have made a mistake.
So we had starting.
But then let's take it. Suppose this is right. What did you? Well,
here's how we did.
He didn't hook up a 1 volt source, so we can't use his results. But if we take this and now calculate. Go ahead.
So here's how we did the nodal. So this is the node we want to find, right?
Yep.
So first we have 1 minus VO over minus J.
Yeah, typically the error is not in the first equation. It's like the stuff you do after that because of all these complex numbers. But let's follow it. So 1 minus VO
minus
over minus J.
over minus J, and then we have
0
this
minus
is
VO over 1J.
over 1J, and then we have
Plus 0 minus VO over 1
right?
equals 0.
And
Yep.
then we multiply it through by J, right?
Okay.
To just get it out of the denominator.
Sure.
That's legal, right?
Yeah.
Yeah. So multiplying by J here.
You're going to get minus 1 plus VO. Okay, good.
Then multiplying by J here.
You're going to get
Minus VO.
minus J VO. Oh, no, minus VO.
Yeah.
Yeah,
No, wait.
Good. Wait, right? Yeah, it's minus VO.
It's minus VO.
See, it's so easy to screw that up.
Wait, I think this we hold on. Was it supposed to be? Unless,
And then
yeah. And then here it's just minus J VO. Yeah. So that's where the arrow is.
Okay. So assuming VO is 1 plus J,
so
we'd
then
still have to find I.
So this would actually cancel these two out.
Oh, there you go.
So then we would have minus 1 minus JVO minus 1 minus JVO equals 0, or 1 plus JVO equals 0? What?
I mean, that doesn't seem right either then.
No.
That's a different answer. That's a problem.
Maybe I'm jumping ahead too fast. Hold on. So, okay.
Uh,
Because that would be, we multiply through by J, all right? And then we have these two cancel out. And then that becomes, minus JVO is equal to 1.
yeah, so VO equals
So VO equals
Minus
1 over minus J, which is just J.
J.
Right?
VO equals J, or does VO equal 1 plus J? Man, we're screwed. So let's see.
So multiplied by J here, and that brings, that's minus plus, because we have a minus 1 under 1 minus V, so that has to be minus 1 plus VO. Then here, got rid of the J, clear that, so it becomes 0 minus VO, so it has to be minus VO. And then the J here, the 1's in the denominator, so it becomes minus VO times J, so it's minus JVO. Now if we have positive VO and negative VO, those have to cancel out. So we have to have minus 1 minus JVO equals 0, or minus JVO equals 1, which means VO is equal to 1 over minus J, or is equal to J.
Another way we can do this, and it is to turn to the computer.
We always go to MATLAB when we have 5 minutes left.
I know. But that is one way to resolve things. And so, like, maybe, so if we took your original equation there, and it'd be nice if we could show that. And so just to kind of check, I would say, all right, I don't want to do any, once I get the initial equation, I want to do the minimum amount of processing in there. So I would say you take all the VO terms and don't touch them, right? So it's going to be VO, it's going to equal all the non-VO terms. Okay, so all the non-VO terms are going to be, in parentheses, it's going to be 1 over minus J, right? That's the first thing. You got 0 in the second one and 0 in the third one, right? So it's just 1 over minus J. And then all the VO terms are going to be, the first VO term is minus 1 over minus J, right? So that's just 1 over J, right? The second one is minus 1 over J, so that is, and the third one is minus 1, right? And we negate that because we didn't swap sides yet. So this says VO is J. You got that right. So the voltage divided. So what did I do? So what happened is that, where did I make a mistake on the Z? Maybe Z parallel, is that right? So let's see, 1 times J.
I think that was right.
J over 1 plus J is 0.5 plus 0.5 J. And then the voltage divider formula says we got 1 volt times let's just make that call that Z equivalent equals answered. And so 1 times Z equivalent over, it's minus J plus Z equivalent, right? I think I did too many things. Minus J plus Z equivalent.
You had a lot going on in that voltage divider.
And it equals J. Yep.
Got J? So it is
It's J. So it's J. So VO is J. So real fast, because we're already out of time, if VO is J, then what's IX?
So Ix would be J minus 1 over negative J.
Move this aside here. Hopefully we can get an answer that agrees with what Duncan has. But the odds of this are really... So it's J minus 1 over, what was it?
And then this is going to be 2J.
So Ix is J minus 1 over minus J, right? So J minus 1 over minus J plus, and that's what? 2VO, because VO is J, plus 2J equals minus I. So I is the opposite of that, right? Well, and this is, so we multiply, I hate doing this, but okay, we multiply by J over J, right? That becomes 1. That becomes negative 1 minus J.
Yeah. Negative 1 minus J.
Plus 2J equals minus I. So J minus 1 plus J equals minus I. So I equals 1 minus J.
And that would just be...
So if I is 1 minus J, then the Z Thevenin is 1 over 1 minus J, which is
Maybe over 2.
Z Thevenin is 1/2 plus
Yeah,
1/2
that's
J.
right.
So
That's right.
0.5 squared plus.
Is that what the answer says?
Yeah, right here.
Okay,
Yeah, that's right.
Yeah.
cool.
And we got the same...
Yeah, because it's got to be the complex conjugate. That's what the answer says.
Close enough. Close enough.
Now I led Duncan down an alternate way. You should see how he's doing it. Let's see if we can find consistency.
So we want the arctan 1.
You guys check this out.
So we got... So it should be 45...
So with Duncan, I made the perhaps unfortunate suggestion that, because, you know, hooking up the test source, it's kind of a pain, right? But you can also find Z Thevenin if you know what V Thevenin is, by finding I Norton, right? And Z Thevenin is V Thevenin over I Norton. And he found V Thevenin. Now, you guys haven't found V Thevenin yet, right? But we should be able to back it out if we know what the power is. At least we can find the magnitude, so we can see if we got this right. So he did the initial work to find V Thevenin when this was an open circuit, right? And now he's shorting it out to find I Norton. And with I Norton, you know, when you're shorting out that current source, you basically have, you know, just one node VO, which again you can use the voltage divider formula on. Now he used, I think you did did you use a nodal equation for that part?
So his answer was really, really close.
No, you did use the voltage divider formula, and you found that the impedance of the problem is with this one is you have a minus J and a J here, and if these are going from VO to ground, because this is now ground here, right? Oops, ground here and ground here, right? So you get minus J times J over minus J plus J. You end up getting 1 over 0 for this equivalent impedance. So that's like an open circuit. So his voltage here is the same as the voltage here, so you got 120. And no current flowing through the 1 ohm resistor, which is pretty odd. So apparently what's happening is current is just sort of circulating around this thing. And
So, Tom, His answer is very, very close to ours. I think it might have just been a rounding error at one
Yeah.
point. Because
0.7, angle 49?
0.707, and the angle.
Oh yeah, that is
The
right.
angle is 45.
Oh yeah,
I could have saved you.
that's probably it. Thank you.
I could have saved you 5 minutes if MIT man would listen to another
Cool.
MIT man.
It takes more heads than one. So I think we're actually converging. That's good. Yep. So that does work. Anyway, a very interesting problem. Thanks, guys. Yes.
Can I add all three of these together and just throw it into here and finish it? Is that legal?
Yeah, you know, that's a really interesting idea. Yes, actually. Once you get them as, yes, do that.
And just solve for IM?
No, wait, because those are in parallel, though. Let's see.
Maybe they thought Imran was a girl's name, and then when you showed up, the first interview, though.
So add AC in parallel with B, then put it into B.
They said that they have actually given to a lot of guys.
I mean, if you find the total power,
Dan, you're not kidding. You're applying everything.
I mean, that does sound plausible, right? If you say, you know, the total power dissipated by this whole network is something, and you know the voltage, it's got to be, right?
Like more women in STEM fields.
Okay.
Try it and see if it compares to the answer. So basically, yeah, try adding all those together.
Adding them all together or just the parallel?
No, adding, because these are powers. So if you add all these things together, I'm just not sure. Let's try it and sort of see. If you add them all together and you have a complex number and you know that VM, it's actually, treat them as, instead of doing S, do S bar, the complex number, which is V times I star over 2. And that's going to be the sum of these things. And then you know that V is 120 angle 30, so you can solve for I star and then do that.
Okay.
Did she leave? Let's see how she did it. So do yours, and then we'll see if it agrees with us. So let's see, Amara got IB of 40 angle 23, and I think she got IAC, and they add them together. So she got 81.57 plus J. 46.7, which looks pretty close. Because the magnitude of that Yep. So hers works. She did it by calculating the current through each of them separately and adding them together. But I'm curious. This just sort of seems like it kind of has to work this way too.
Add those by just adding.
Adding them as complex numbers.
So add these.
Yeah, adding them in rectangular form. Yeah.
6,600. I had done it, erased it.
6,600, yep.
Plus 800, 1,300.
Okay, so that's the total power.
just solve for I.
So, yeah, so then solve for I star and then take the complex conjugate of that answer. So basically, so this is basically just 60 angle 30, right? So, so this divided by 60 angle 30. And this will be 11.14 minus 30. Yeah. Okay, so then I is supposed to be 112. It didn't work out quite right. The answer is supposed to be it has a magnitude of like 93, angles 29 degrees. That was really, so I wasn't sure about that, and I think it's probably just because you don't know, if you're just adding those together, maybe that's assuming that they're in series or something, or what? Yeah, I guess it matters how they're arranged. So the way Emma did it, you can come over here and look at hers. She broke it up into the parts that are pretty clear. So like, VB is directly got the 120 angle 30 on it, right? And so so IB is just going to be or actually she did this thing. The SB complex power is the voltage times IB star over 2, and so she and that's the same thing you got, and then she solved for IB star, and then just found found IB, and then for the other one, she added these two together. I guess you can only add them like that when they're in series or something, because the addition of these two, forms a net impedance, which is the sum of the two impedances too. The thing is, when you have them in parallel, that's a different combination of impedances. That's probably why it didn't work, because you had that one guy in parallel. So you add these two together, and she found SAC complex number, which was the sum of SA and SC, and that's the voltage across the whole sum of those. And so then she solved for the IAC branch as that, and then she added those two together. So that's just a slight change in what you did, but that was a good idea. Yeah. Yep. Sure.
You want me to erase it?
Yeah, you can erase it. I got it all on film now. Thanks, Rob.